Hello, this is Professor Kuehn. In my last lecture, I talked about how Hans Christian Oersted had carried out some experiments to measure the effect of an electrical current on a magnetic compass needle. Specifically, in my last lecture, we talked about the third experiment, where he suspended a compass needle from a current-carrying wire, and how he noticed that when the wire was made of different materials, the effect, the turning of this magnetic compass needle, was somewhat diminished for more resistive wires and more pronounced for more conducting wires. And in that lecture I said I'd like to make a diversion, talk a bit more about the relationship between electrical potential, electrical resistance, and electrical current. So that's what I'm going to do in this lecture. So let's talk for a moment about how batteries work. Well, a chemical reaction in a voltaic battery is caused by electrical charges accumulating on the terminals. So if we had a trough, like what Oersted uses, that's full of acid, remember he was using water, sulfuric acid, and nitric acid, and he places these plates in the trough. I'm just drawing one of the cells of his battery. He had multiple ones connected to each other. But if you had a copper plate and a zinc plate that is immersed in this fluid, this acidic fluid, what happens is that the positive charges move in this direction due to the chemical reactions and give the copper plate an overall positive charge, and the negative charges, the negatively charged ions, move in this way and deposit electrons, if you want to think about it in terms of protons and electrons, on that plate. And so the copper plate acquires an overall positive charge and the zinc plate acquires an overall negative charge. So this is driven by chemical reactions. So chemical reactions in a voltaic battery cause electrical charges to accumulate on the terminals. That is the point that's being made here. Now, these terminals acquire an electric potential difference, and this is today measured in volts. So the terminals acquire an electric potential difference. In our next reading, we're going to read ampere, and he calls this an electric tension, but the modern term is electric potential difference. And today this is measured in volts. So volts is a measure, a unit of electric potential difference. You know, we often just call electric potential difference voltage. This is a bit like calling measurements of distance yardage. It's taking a unit that you're measuring it in and just calling the measurement by the unit you're using. It's also like calling a weight a poundage. So oftentimes I'll use the word electric potential, sometimes I'll use the term voltage, but that's what I mean by that. Now, if a wire is connected between these terminals, let's suppose you hook up a copper wire. Let's make copper wire red. If you hook up a copper wire between these two terminals, what is going to happen is there's going to be an electrical current that is driven through this wire. Okay, so there will be an electrical current that circulates around in this wire. And we'll talk more about the convention of why we say the current is flowing this way and not the other way. That was a convention that is going to be articulated by ampere in our next reading. But there's going to be an electrical current driven by this electrical potential difference through the wire. Okay. So let me just write that down. If a conducting wire, such as copper, is connected, an electrical current, and this is typically denoted by the letter I, is driven through the wire. Okay. Now, how much electrical current is driven through the wire? What's the magnitude or the size of this electrical current? Well, it depends on a couple of things. It depends, first of all, on the voltage of the battery, and secondly, it depends on the properties, specifically the resistive properties of the wire. So the voltage that's being applied to this, that's trying to drive the current through it, depends really essentially on the strength of the chemical reactions, or the rapidity with which these chemical reactions happen and can accumulate the positive and negative charges on the terminals. Whereas the electrical resistance is a property of the wire itself. These two factors, the voltage and the electrical resistance, and how they affect the current, is captured by a formula now known as Ohm's law, which relates the electrical current flowing through the wire to the electrical potential difference that's trying to drive the current and the electrical resistance of the wire itself. So this is Ohm's law. Sometimes it's written as V equals IR. Here I'm writing it as I equals V over R. So this is, you might think of this voltage or electric potential, it's sometimes called the electromotive force. You can see there, electromotive force, there's the word electro. It's a force that tries to move electrical currents. And again, it depends on the properties of the battery itself. Whereas this is the electrical resistance of the wire. Okay, so what does the electrical resistance of the wire depend on? The resistance of the wire, we'll come back to this more later, but it's good to give you a heads up. Resistance of the wire depends on a few things. First of all, it depends on the length of the wire. So the longer the wire, the more resistance it offers to electrical flow. So that's one factor. Another one is the diameter of the wire, or the gauge of the wire. So a narrower wire provides more electrical resistance. It's almost like having a hose, right? If you have a pressure trying to drive water through a hose, a very long hose is going to offer more resistance to the flow of water. And likewise, a very narrow diameter hose is going to offer more resistance to the flow of water through the hose. So these water analogies sometimes provide some insight into electricity. And finally, the material of the wire. So certain materials are better able to carry electrical currents, for instance, metals like platinum, silver, gold, and other materials are less likely to carry electrical currents. So insulators would be an example, like glass or wax. So the resistance of the wire depends on these factors. These are kind of factors that have to do with the size. These are extrinsic properties of the wire, and the material is an intrinsic property of the wire itself. Okay, so why are we talking about this? Well, because remember what Oersted is doing is he's hooking up this battery to drive an electrical current through this wire and looking at the effect on the magnetic compass needle. And in his experiment 3, he found that when you connect different types of wire to the electrical terminals of the battery, the effect on the compass needle is increased or decreased depending on the kind of wire. So presumably what's happening here is when the material that you're making the wire out of is a more resistive wire, like iron, let's say, the current, if the resistance is larger, then the current is going to be smaller, and that electrical current is what's causing, in some sense, the effect on the magnetic compass needle. Okay, I'm going to stop there, and in my next lecture I will talk about his fourth experiment on the effect of an electrical current on a magnetic compass needle.